So this time, we are going to take a square piece of cardboard. It's 12 by 12, and we're going to cut the corners out and fold it up. If you remember, we kind of talked about that in pre-cal, what it looks like. You take a piece of paper, and we cut the four corners out, and then we fold everything up, and it makes this little box without a top, okay? So this is that same situation, right? So we've got this, if you turn your pen on, the square piece of cardboard. That's 12 by 12. And we're going to cut out these corners and then fold it up, okay? Okay. So we don't know how tall these corners need to be, right? So I'm just going to call those X. All right. Now, we want to find the dimensions that will result in the largest volume. So volume is our maximizing function. How do we find volume of a box? Length times width times height. Okay, length times width times height. So this is where we have to think for just a second. If we think about our box where we've cut the corners out and we folded it up, okay, my original length was 12, but I took what out of it? 2 X's, okay? So I'm going to have 12 minus 2X. And then what about the other side? It's going to be the same because it's a square base, right? What's the height? It's that X. It's that little piece we fold up, okay? So where we fold it up, it's that height of X, okay? Now, now we've got it down just to two variables, volume and X, the little piece we're going to cut out. We can multiply all that together, all right? So I'm going to start with these first two. It's going to give me 144 minus 48X plus 4X squared. Okay, and then we're going to distribute that X. So 144X minus 48X squared plus 4X cubed. All right, so it's kind of a nasty equation, but it'd be all right. Okay. Now we're ready to take a derivative. All right, we're ready to take a derivative. So that would give me 144 minus 96X plus 12X squared, and we're going to set it equal to 0. So we've got to find those critical points, okay? It's a quadratic. We're going to need to factor it, but it would help me a whole lot if I didn't have all those big numbers in there, all right? Is there a number that would evenly divide 144, 96, and 12? 12, yay. Okay, so 12 would divide all of those. So if I divided everything by 12, that would give me 12 minus 8X plus X squared equals 0. That's a lot easier to factor, okay? And so if we think about this, we're going to get X, let's see, minus 6 minus 2. That give me X squared minus 8X plus 12. Yep. And so I get 6 and I get 2. Okay. I get 6 and I get 2. Now, I like the candidates test on this one still just because. So let's think about that for a little bit. What our domain could be for X and for volume. What's the smallest thing I could cut out?
0.
0. Okay. Now, tricky, what's the largest thing you could cut out? 6. Okay? Because you've got 12 minus 2X. If that dimension's 0, then, I'm out of luck. Okay? And so I put my 2 in there. And so now we go back to our volume formula, and we plug all of that in. If I plug in 0, I'm going to get 0. And if I plug in 6, I'm going to get 0. So we know the maximum is going to happen at 2. Okay, and so let's figure out what that volume would be. Let's see, 2 times 2 would be 4, minus 12 would be 8. It'd be 64, right, times 2, 128, right, is my max volume. Now, let's go back and look at what it asked me for, okay? What did it ask me for in terms of my answer? The dimensions, okay? So we're going to go back up here to this original volume equation and get these 3 dimensions, all right? We know x is 2. What does that leave the other 2 sides to be? 8 each. Yep. So we would say the largest volume occurs with the dimensions and you can say 8 by 8 by 2 and then just put feet at the end. Okay, so you don't have to put feet on each one. How did I get those numbers? Okay, so X is the piece we're cutting out. All right, if we want to be able to fold a box up, 0 would be the smallest thing I could cut out. Okay, the reason 6 is the largest thing we could cut out is if we look at these dimensions, if I plugged a 6 in for X, that would give me a 0 for the side. If I did 12 minus 2 times 6, it's whatever's going to make that parentheses 0.
What about those
The dimensions part. So I knew that it happened when my max happened when X was 2. So I went back and I plugged 2 in to each piece of the volume formula, which were my dimensions, my length, my width, and my height. Yeah. Okay. Let's do another one that's similar. Okay, that's similar. But this time we're going to close the top on the box. Bless you. Okay. Okay, we're going to close the top on the box. Does this make a huge difference in what we do? Okay, a little bit. Okay. So we've got a square sheet of cardboard with side length 60 inches. Right. It's folded into a rectangular box with a lid. 4 squares with side length X and 2 rectangular regions, all right, are discarded in order to fold the box as shown. For what value of X is the volume of the box a maximum? They did tell me volume is length times width times height, so they at least gave me that, which was nice. Okay. So now let's just kind of mess around a little bit, all right, with what we've got, and let's see if we can figure out what we're going to use. We know this whole thing is how much? 60. Okay. And then this piece is 60 as well. Okay. So let's take a look. And we know these little measurements are X, okay, because they told me the little pieces were X. All right. Let's think about this right-hand side. Okay. And the whole big piece of cardboard on that right-hand side, okay, or left-hand side, all right. I started with 60, but what did I cut out of it? 2 X's, okay. So that's definitely one of my dimensions, okay. We're going to deal with that other one in just a second, but what about my height? What's the height still going to be? X, okay. So all we've got to figure out is this bottom side, but the bottom side's a little bit different, okay, because not only have I taken some X's out, I've also got this rectangular region that we're taking out. You see that piece? All right, so we got a lot less this time, all right? We got a lot less this time. Any thoughts about what this one's going to be? So it's the same as which rectangular region?
The bottom, what will become a side?
Yeah, what will become a side, okay? So those match, all right? Those match. So let's think about what we would have left, okay? We know for sure I'm going to take out 2 X's. Would you agree with that? If we're looking at this bottom side, there's an X, there's an X, okay? And then what does that leave me? How many rectangles? 2. But I don't need 2, I only need 1. So what am I going to do with it? Divide by 2. Okay? So 60 minus 2x and divide the whole thing in half. I don't need the whole 2 rectangles. I only need one of them. Okay? Because if I took out the 2 squares that were my x's, it leaves me those 2 rectangles. Okay? And I don't need 2 of them, I just need 1. So we cut it in half. All right, take a second look at that. That's different. When we put a lid on it, it changes that side. Okay? It's always split in half. Heads up. Okay? It's always split in half. So let's simplify that a little bit. Okay? So my volume's going to equal 60 minus 2x times, if I go ahead and divide that parenthesis by 2, it gives me 30 minus x and an x. Right? I really think on this one, getting the equation is the hardest part. The calculus after it, it's not that bad. Okay, so let's multiply. That's going to give me 1,800. Let's see, 60x, so minus 120x plus 2x squared. And we're going to multiply by x. Okay. All right, so that's going to give me 1,800x minus 120x squared plus, oops, oh, I said 4, plus 2x cubed. Okay, so there's my volume formula. All right, now what are we going to do? Take a derivative. Good. Okay, so I'm going to get 1,800 minus 240x plus 6x squared. Please let that be divisible by 6. Is it? Yes, we could divide the whole thing by 6, thank goodness. So that's going to give me, I'm going to rewrite the order. It's easier for me to factor. X squared minus 40x plus 300 equals 0. All right, so let's factor. Negative 10 and negative 30. Multiply to 300, add to negative 40, so we get 10 and 30. All right, if we think about our candidates test, we've got x and we've got our volume. Okay, smallest x we could pull out, 0. Okay, largest x we could pull out, 30. Okay, 30. And then we're going to check 10. We know that first 2 are going to give me zeros. The first one and the last one are going to give me a 0, which is nice. Okay, and then if we plug 10 in there, what do we get for our max? It's 200 times 48,000. I did that in my head, which is dangerous. Okay, what did it ask me for though? Yeah, what x value? Okay, so the answer is x would equal 10, and did it give me, yeah, inches. All right. What do you think so far? It's okay. It's not the easiest, not the hardest, but all right. Getting the equation is typically the toughest part. The calculus is usually not that bad. okay? Because you're taking a derivative, setting it equal to 0. We can use a candidate's test and move on, okay? Let's look at a box problem that's a little bit different, okay? Where we're not cutting out something, all right? We're going to talk about minimizing cost. Okay, so this time we want to construct a box whose base is a square and that has a volume of 36 cubic feet. The material used to build the top and bottom cost $8 per square foot, and the material used to build the sides cost $6 per square foot. We want to determine the dimensions that will minimize the cost. Okay, so my equation we're going to write is a cost function. Okay. It's not area, it's not volume. I think we'll use all those things, right? But we're going to minimize a cost function. So we're going to eventually have to write a cost function. So let's start. We're going to start with a square base. And we're going to build a box. Okay, now y'all don't laugh at my box. This is how I draw one. Okay, all right. It's got a square base. All right. Okay, thanks. So if we think about the top, okay, think about the top, all right, how do we find volume of this box? Length times width times height, okay, which has been nice. We do it the whole time, okay. And so if we think about the base, all right, we know the volume is what, 36? Okay. If we think about the base, it's just x squared. Okay, x times x is just x squared. Okay, how many bases do we have? 2. Okay, we have a top and we have a bottom because that's what it talks about, to build the top and the bottom. So the top and the bottom, we have 2 of those. So we know in our cost function, we're going to have 2 of the x squares. And how much do they cost to build? 8. Okay. All right. Now let's think about those 4 sides. It didn't tell me that it was a cube. All right. So those sides could be rectangular. All right. So we need to know the height. Okay. We need to know the height of that box, which would be this piece. Okay. And so if we think about the side, how are we going to find the area of the side? X times h. Okay. How many of those do we have?
4.
We have 4. Okay. So plus 4xh. And how much do they cost? 6. Okay. So we're getting closer. All right. In our volume formula, we know the length and the width are the same. And we have the height. Okay, it's equal to 36. So x squared h is equal to 36. If I look at my cost function, which I'm going to take the derivative of, I've got more x's than I do h's. If I could get that h out, it would help me. Okay, so could I use the volume formula to get my h? Sure. H would be 36 divided by x squared. So we're going to replace that over here. Okay, so 8 times 2 would give me 16x squared plus 24x, and then my h is going to be 36 over x squared. All right, so we just keep replacing variables, nifty substitution, all right, doing all the things. And let's simplify that equation again. So that's going to give me 16x squared plus 24 times 36, 864. And then x over x squared. Yep, x on the bottom or x to the negative 1. Okay, so there's my original function. Okay. Now that we have the function, that's the hard part. Okay, let's do the derivative. All right, so c prime. I'm going to get 32x. Let's see, that's going to be x to the negative 1. So minus 864 over x squared, or x to the negative 2. We're gonna set it equal to 0. No, we don't wanna solve that one. Okay, we did one like this yesterday. What's the best way to get this into something we can solve? Yeah, move the fraction over so you can do a proportion. Okay, let's bring the fraction over so we can do a proportion. So I get 32x equals 864 over x squared, or 32x cubed equals 864. All right. Divide, I believe that's a 27. And then we take a cube root. And so what does x equal? 3. Yay, I like it when it's a nice pretty number. Okay, so x is 3. All right. This is a finite thing. It's a box. All right. And so let's walk through what our dimensions could be. Okay, so x and our cost. Absolute lowest would be 0, obviously, but that's not going to work because if we look at our cost function right here, what's going to happen when we divide by 0? Yeah, paper explodes. So it's going to be undefined, but that's okay. Okay. We know we're going to use 3. That's the one we solved for. It's my critical point. Okay. Now think for a second about the max. Any ideas on what the maximum x would be? I'll give you a hint. It goes back to your volume function. (18 times 18 times the height), that's going to be more than 36. This has to be 6, right? Because if x is 6, what would the height be? 6 times 6, so x matches. 6 times 6 would be 36, so h would be 1. All right, so it has to be 6. Okay, it has to be 6. That one's tricky. All right. Now, let's plug into our cost function and let's figure out our values. Okay. So let's plug in 3. So I have 16 times 3 squared plus 864 divided by 3. You can use your calculator for that. I would not do that in my head. C. Yeah, always into your cost function. If you use a sign chart, you plug it into the derivative. If you use candidates, you plug it into the original. Okay, did you get 432 for 3? And then for 6, 16 times 36 plus 864 divided by 6. I believe it's 720. Okay. Now, what did they ask me to do with the cost? Minimize. Okay, which one's going to give us the minimum? 3. Okay, so this is the minimum cost. It asked me to find dimensions. Okay, it asked me to find dimensions. So we're going to go back to our volume formula, all right, to do that because I need x, and I need a height. Okay, well, we found x. Okay, the dimensions would be okay, if I plug it back into my volume formula, x is going to be 3 by 3. And then to get my height, I'd take 36 and divide it by 3 squared, which would give me 4. And we're talking about feet. Right here, I use this height equals 36 divided by x squared.
How'd you get 6 for the last one?
For the last one, I looked at the volume, okay? My volume is exactly 36, okay? And so if I let x be 6, 6 times 6 is 36, that would make my height 1. Yeah, that would make my height 1. Yep. Because in order for it to be a box, you got to have something. Yeah. Okay? Good question. Let's do one more. We're going to call it a day. Okay? All right. Here we go. The equation y equals x squared plus 3x minus 5 represents a parabola. Name the point on the parabola that is closest to the origin. Woo! I know, this one's tough, okay? It's because we got to really think about what it's asking me to do, okay? So I don't know exactly what this parabola looks like, but does it open up or down? It opens up, okay? And in fact, I'm really not even really sure where it's at on the coordinate plane off the top of my head, okay? So I'm just going to graph it like that, okay? I want to find the point on that parabola that is closest to the origin, okay? So I want the point that is closest to the origin, all right? So is that a maximum or a minimum? We're looking for a minimum, okay? So we're going to minimize the distance between the curve and the origin. Okay, so that's thinking of what we want to do. We want to minimize the distance. So we're going to need the distance formula. We've not used that bad boy in a long time. How do we do that? Yep, change in x squared plus change in y squared. Okay, now the good news is I happen to know one of my ordered pairs. What's that ordered pair that we want me to get close to? 0, 0. Okay, so I'm going to replace that. So d is going to equal the square root. X minus 0 would just be x squared, plus y minus 0 would just be y squared. Well, I'm getting closer, okay? Still got one too many variables.
Y equals x squared plus 3x minus 5.
Yep, they told me y was x squared plus 3x minus 5. So I have d equals the square root of x squared plus x squared plus 3x minus 5 squared. Okay, so that's what they gave me. Now, this would be a calculator question, okay, because we're going to get some crazy decimals on this one, all right? So what we need to find is where d prime is equal to 0, and I'm going to let my calculator and my graph do that for me. Okay, I'm going to let it do that for me. Let's go over to our calculator, and I'm going to do math 8 up in my derivative. Bless you. Okay, so math 8, and then I'll put that big function in there, second square root x squared plus parentheses x squared plus 3x minus 5, and I'll close that parenthesis and square it, and then I'm going to do that for all x. Okay, I have no idea what this is going to look like when I graph it in just a second. Okay, I'm going to zoom 6 it and pray for the best. Okay, so zoom 6. Oh, yay. All right, so now let's talk a little bit about what we see. Okay, how many zeros do you see? 3. Okay, I see 3. And so let's look at them. Okay, let's look at them.
How come you guys do 6? What's that do?
It's just a standard window, 10 by 10. Yeah, that's where I usually start, and then if I need to see more things, I go in and adjust the window. Yeah, if I'm doing something trig and I'm not quite sure what I need, sometimes I'll zoom trig. So, okay. All right, now I want you to think for just a second about this graph that we're looking at, okay? We're looking for a minimum, okay? Which means my derivative needs to change from positive to, no, let me say that right. From positive to negative, is that right? I'm struggle bus. Yes, from negative to positive for a minimum, right? So the derivative needs to go from negative to positive. That would mean I go from decreasing to increasing, all right, on my actual graph. Okay, so if I'm going from negative to positive, there are only 2 points I have to check, even though there are 3 critical points, okay? The first one's going to be this one over here around -4. All right, and then I don't have to check the one that's just before -2 because that goes from positive to negative. That's not what I'm looking for. That would be a maximum, okay? And then I'm going to check this one over here at +1, okay? So second trace, and I'm going to choose a 0, and then I want to get to the left of that first one and hit enter, get to the right and hit enter, and then enter again. And so my 0 is at -4.041 or -4.040. Write that number down. Okay, so you got it. I don't care about that critical point at -1 point something because it's not going to be a minimum, right? Because it goes from positive to negative. So let's jump over and let's do the one that's over at before 1. So we're going to do a 0, and then we're going to get to the left, and then get to the right and let it guess for me. So about 1.51 or 1.52. Okay, whichever way you wanted to do that. All right. So since those are the only 2 values that we need to check, okay, let's go back to the regular screen, and we're just going to plug it into the distance formula. All right, to see which one gives me the smallest distance. All right, so if you wanted to, you could go to y equals, and in y2, just type in that crazy radical, all right, because that's my distance formula, which is probably what I would do. X squared plus parentheses, x squared plus 3x minus 5 squared. Okay. And then I go back to my home screen. I'm going to use my function thing, okay? So alpha trace, and this time it's in y2. And I would plug in that first value we found, which is -4 point, oh, I need a parenthesis, sorry. Let's see, -4.040, okay? And then I do it again, alpha trace, y2, parenthesis, and I would plug in 1.151 and hit enter. Okay, we're looking for the minimum distance. Which x value gave me that? The 1.151. Okay, so then it says name the point on the curve. Well, we know the x value is 1.151. Okay, to get the y value, it's on the curve. We're going to use that basic equation, x squared plus 3x minus 5, okay? And I would just write it down right here. 1.151 squared plus 3 times 1.151, and then minus 5. Okay, so that's going to give me my y value. So my ordered pair is going to be 1.151 and then comma negative 0.222. All right, so lots of calculator work there. All right, to make that happen, lots of calculator work.
So what was the number that we got when we plugged in -4 and 1 to?
4.118.
Yeah, what is that?
That is the distance from the origin.
Okay.
Yeah, because we're talking about the distance from the origin. Yep. And the smallest distance was 1.117. Okay, good question. There was just so many numbers right there. It was hard to know which one was which. Okay. All right, so let me jump over here and write all that down so we got it. Okay. So our critical points, using our calculator, were at x equals -4.040 and at 1.151. Then we got our distance. That's what we plugged into the actual distance equation. We got 4.118 and 1.172. So this was my minimum distance. Okay. Then right, it asked me for the ordered pair on the curve. So the point on the curve was this. It was 1.151, and its y value was negative 0.222. Okay, so that just went back into that original parabola. Okay. All right, so your lesson practice are those same problems. Okay, so I want you to go back and I want you to look through those. What I think we'll do is on Tuesday when we come in, we will work on, I have a worksheet that has some more of these on them, and we'll work on those in class, okay, together, just to make sure that we're feeling good about how optimization works and all the different ways to approach the problems, okay? And then if you would, I want you to do the wrap up, but it was for yesterday. Okay, so it was from 116. If you would do that wrap up for me and then just work on those same problems, okay? Do what?
It's not there anymore, the wrap up.
Oh, did I take it off? See if it's on today's lesson. Did I move it? No, I just deleted it because I'm an idiot. Pause. No.
Never say that about it.
Let me go back here and fix it. It's been a day. Okay, hold on just a minute.